So that's the last one. Let's show the empirical evidence then. So first the data and the variables. The data come from Fama and French, from Kenneth French data library. That's the returns on the S&P, HML, and also the market premium from July to December 2019, 26, 2016. I use also two price risk proxies. Actually, I'll join them into one. They are the Dow Jones Book to Market. It starts in 1921, and the net equity expansion starts in 1927. Those are the only two variables that forecast the market premium in sample, right? The Goyal and Welsh find that nothing works out of sample, but in sample they forecast the market premium. That's why I use them. The net equity expansion is a problematic variable because it really has no theoretical reason to be a price risk proxy. I use it to avoid uh, like the impression of data snooping or something. Uh, but it is actually this is actually not a price risk proxy, a real price risk proxy, and it's not problematic. Uh, First of all, it doesn't work very. The Dow Jones Book to Market alone works better. The net equity expansion doesn't work in other settings. Also, it's not really a price risk, but it's not a big problem because what I do is I just take the first principal component between the two variables. So I don't really repeat because otherwise I would need to repeat the exercise using one and using the other. What I find is that I can actually just take the principal component, the first principal component of the variable, that's the PC1 here. It is the only one that actually forecasts the market premium sample at the monthly and the yearly frequency. The other principal component, the second one, doesn't forecast anything. So I only use the first one, right? So it's basically to say, well, those are the underlying variables, but I only use this one here. I only use the first principal component. Um, the second point is to show that these variables actually forecast the size of the value premium. And then it's true if you use the variable each month, which is not exactly what the theory says, but if you use each month, it has this positive correlation in line with the hypothesis that this is a price risk proxy. And if you use it at the formation date, so I fix it every June. Now the variable has a yearly frequency. It actually forecasts, of course, that it's not statistically significant, the difference, but it forecasts actually a little bit better than if you use the monthly variables. Of course, that I don't make much of this difference, and I use only this one here, right? Because this is what the theory says, that what matters is the price of risk at the portfolio formation date. But because they're so persistent, then it also works if you use the monthly variable. Right. So this is the first one, is to show that it actually forecasts the two premiums. The next step is to tell what is a high and a low price risk state. And here, what I want to do is I want to calculate a backward-looking percentile classification. So I'm going to look at what the variable is. That's the PC1. So what's the value today? What is the average until yesterday? And then I'm going to calculate what is the percentile of this variable here, given everything that we know of the variable until that date. So what's at what percentile the variable is? Like, is it at the top 90%, top 80%, bottom 10%? So this is the actual variable that I use here to tell, well, the prediction of the model. That's the first prediction that we had there in the classification, in the solution of the puzzles, is that there is a threshold for the size premium, a threshold for the price of risk, above which the size premium is actually significant. So it's going to be 0 below this threshold and positive above this threshold. That was the model prediction. And then what I say is that the model is going to be, it's a simplification. It's going to be 0 if the price of risk is below a certain level, and then it's going to be whatever is the average, the past average, when the price of risk is above a certain threshold. So let's say that I take 10%, it's going to be what I have above 10%. If it's 50%, what I have above 50%, and so on. Now, the the choice that I will make to choose what is lambda star here, lambda star mean squared error is going to be, well, I'm going to minimize the mean squared error of this prediction here, right? So if this model is correct, what is in a grid of percentiles, what's the percentile that minimizes this thing? And I also wanted the size premium is significant. So there's an extra, it's not really binding actually, but it's an extra restriction that I have. It is actually binding for the first principal component. It's not binding for the if I only use the Dow Jones booked market. So how does it look like? Like really look like? I don't use this, so these two are just informative. So that's the Dow Jones booked market. You would have here more or less. That's the lambda star SMB. So it would be here. If you use the net equity expansion, it's not really good, as you see here. It would have very strange type uh, of pattern here. But for the first principal component, it is here at 80%. So if it's above above the 80th percentile, then then the size premium is significant. If it's below, it's not. So this is the point, right? I will talk later about these gray lighter points here. So this is the point where this function here is minimized, and that's the one that I'm going to use in the test. So in the formal test, what I want to see is if the price of risk, if the value premium spread, or the spread between the value premium and the size premium is, that's the prediction in the correlation hypothesis, right? So the spread is actually positive if the price of risk is low, and the spread is going to be negative if the price of risk is high. And what we find is exactly this in the data, right? So the spread is actually significant in low price of risk states. It's interesting that if you look at the whole sample and you compare the size and the value premium, it's not significant, the difference. The value premium is a bit larger, but it's not significant. But if you look only in low price of risk states, the difference is actually significant. So the first part is right. That's this one here. And then the second part, which is that the size mean should be negative, is also right. So it is true that you end up with a positive and a negative result. And most importantly, I think I didn't put here. Yeah, I didn't put here. But most importantly is that this prediction here implies that the difference must be negative, right? So the difference between the spread in low price of risk state and the spread in high price of risk state is negative, whereas the difference based on the causation theory is the opposite. So if you compare the difference between these two, this difference is 1.18, and now it is significant. It is significant at the 5% level, because this is a one-sided test. It's not a two-sided test. It's not different from zero zero against different from zero. It's actually smaller than zero against bigger than zero. So this is actually a significant test. And even if you assume that the variances are different, the variances in these two groups are different. If the variances were the same, then it would be also significant anyway. But then I would then need to explain and stress that this is a one-sided test, right? So this is the actual formal rejection of the model. So the test in the paper is this one here. So it's the test that can tell, based on this test, you can tell, well, causation theories cannot be right. Of course, with all the caveats that come from the assumption that I made about parsimony on the models, that the models need to be parsimonious and etc. Right? So based on all of that, and based on the dark matter in my own model, which is that the size, not the size, book equity is a good proxy for expected cash flows for a small subset of firms. Right. So based on this type of, given all these assumptions, I can actually formally reject the hypothesis that causation theories work, and I can accept that correlation theories work. Okay, so this is the formal test in the paper. That's the main test in the paper. Now, adding to this comes all the qualitative results, which I actually think that are even more convincing. Because if you look at the model predictions, for example, if you look at what happens, what the model predicts to happen, that should happen in spanning regressions, then we already have this, right? So the HML is bigger. That's common for both theories. But then we need that the beta on the SMB is going to be small. Let me just show the table already. So the beta SMB here what I'm doing is I'm regressing the SMB returns on the HML. So I'm using the HML to span the SMB portfolio. So what the theory says that in low price of risk states it should be very low R squared. In high price of risk states the R squared should be high. And this is exactly what we find. It's 0 here and 13% here, right? So that's the first, that's the factor structure. And this is just based, here we don't have any dark matter, right? It's just based on the fact that they capture the same risk. And in low price of risk states, the S&P portfolio just doesn't carry any risk because we saw already that in the first figure, the main figure that I showed you, the picture showed that it was a flat line between risk and price, right? So no risk captured by S&P by the S&P portfolio, no factor structure, a lot of risk, a lot of factor structure, right? The same thing, the same explanation is the same mechanism explains why the beta is much larger here than it is here. Essentially here is 0, and then you have a very large beta here in these states, right? So we have a very strong factor structure, and the betas are also very large. If we add the market premium to the regression, you still get the same result. It's essentially 0 here, 0.2 here. The difference in the factor structure doesn't increase as dramatically as here, but it's basically the market premium, entirely based by the market premium, right? So this 9% here is just the market premium, nothing related to the size. And even after controlling for this, you still have this strong relation between the SMB and the HML, right? So this confirms when you regress the SMB, this confirms the predictions here when you regress the SMB on the HML. And now remember that the prediction in the causation theory is that the R square should be the same because the two portfolios have constant risks. So in one state or in the other, it doesn't matter. Like the shocks that affect one and the other, they are always the same. The factor structure should be the same. And that's completely not the case. But then, as I said, it's not a formal rejection of the theory because I cannot really say that this is different from 0, while this is not, or this is different from that, or these parameters here. This is very noisy, so I cannot really say that they are different. It is a very small sample, right? 108 observations is very small to make the type of formal test that I would like to. What else? The other thing is about the size premium. That's the first thing, right? To confirm that the mean squared error predicts the size. There's only 10% or less than 10% of the sample in which the size premium exists. This is 1.3. That's monthly return, so that's very large in percent. So it's 1.3% per month in these states here, and then essentially 0 in the remaining states. And this confirms the previous paper that I had. Right? But that also confirms that the threshold actually splits the sample into 0 and difference from 0 premiums. Right. What happens if we do the opposite? If we regress the HML on the SMB? Well, now we can look at the beta on the HML is going to be again essentially large here and nothing here, just as before, right? It's the same. And we can also look at the alphas. And that's one important point, is that the alpha in low price of risk states, the alpha in low price of risk states is going to be larger than the alpha in high price of risk states. And that's exactly what the model predicts based now this part, the part that relates to book to market needs, that's where I need the dark matter assumption. So in this part here, we actually have that this is true as long as book to market, as essentially book equity is a good proxy for expected cash flows for a small number of firms, not for all of them, right? So we have that the HMR portfolio is positive and significant in low price of risk states. So the intercept is positive and significant in low price of risk states, and it's insignificant. It's negative but insignificant in high price of risk states. Um, that's another point. Yeah. Well, the R square obviously it's just the same, right? It gets even more dramatic even after you control for the market premium. It gets an even more dramatic difference here between nothing, essentially nothing here, no explanation of the value premium here in low price of risk states, and then 33% in high price of risk states. So it gets even more dramatic, the change in factor structure that you have from one state to the other, which is inconsistent again with the hypothesis that the risks are just the same in both states. One important point, very important point, is that the S&P portfolio spans the HML portfolio in these states, right? But then you might not be very convinced because, well, the size, the value premium is already insignificant in these 108 months. So let's extend this. Let's relax, and that's the one that I wanted to tell you about again. Let's relax this mean squared error point here, the threshold that used to select the high pressure. So let's relax it. So let's relax it for, actually it's this one, the relevant one. Let's relax from 80% to around 67%. And if we do this, by doing this, we are going to get, the way to get from here to here is to find the maximum closer to, to relax this just enough so that the value premium is significant in this part of the sample. So if we do this, it actually increases a lot, the sample. It increases from 180 to 108 to 246. So it's more than 100% increase, almost 150% increase. The value premium now is larger, as it should be. It's larger than the. Of course, I don't make it that I cannot test the difference and say that this is really larger, but at least the point estimate is large. It is significant. And now the point is that if you try to regress all these months, and there are lots of months here that are not exactly a high price of risk states, right? So if you regress these months again, these returns again on the SMB, you're going to find exactly what we should find, right? So strong, large beta, strong factor structure, only in these states. There is this strange result or negative result here in these low price of risk states, less than low price of risk states. But the main point is this one here, right? Because the classification, the correct classification is the other one, is the lambda star MSC, and we already saw that the results hold. In these results here, in this table here, what we see is that the S&P portfolio still spans the HML portfolio even in these states, right? So it still spans the results, and it spans it even it's even stronger if we control for the market premium, right? It's completely unspent here, and now we have something that's even smaller than 0.3 and with a smaller t statistics also, t statistic. And it's also important that you have more months here, so it would be easier to actually get something significant in a larger sample than in the smaller sample that we had before. The factor structure, it's everything. Everything again is everything is the same here, right? Qualitatively the same as before. All right. So in summary, what have we learned in this paper? Well, we first learned that the present value identity, it actually explains the size and the value premium, right? So it's just the present value identity. We also learned how to model the risk of price-related portfolios as functions of the price of risk. And it's important that it set functions at the portfolio formation dates, right? Because it's not like models that just let's say forecast the return based on what's the price of risk. It's not a factor timing in this sense. It's about differences in portfolios. So different portfolios have different risks. So what you need to do is to forecast the risk of the portfolio. And that's the point here. So now we know how to model the risk of the portfolio. It's not the risk of the month, right? That's an important point because there is a discussion that I had with some referees also about whether to use like dummy variables for for given months and so on. But that's not the point, because the point is that the portfolios are different. It's not just that the months are different. So you cannot run a pooled regression, for example. What we also learn is that book equity is exclusively a proxy for expected cash flows. It's none of these stories about relations, intrinsic relations between risk and book equity, or risk and book to market, and so on. Unless, of course, I'm not saying that it's completely impossible to come up with a causation theory that says, well, book equity is intrinsically related to portfolio. Of course, it is possible if you make if you make use of enough of these dark matter assumptions, of these untestable assumptions, then of course you can explain even the type of results that I have presented here, right? But what I mean is that, at least in a parsimonious way, in which you don't make assumptions, strong assumptions about how the risk of the portfolios change from from low to high price of risk states, how the relative risk prices change from one state to the other, or how the function, all those assumptions that I made when that I avoided when I made the predictions or the implications, when I calculated the implications from causation theories. Of course, if you relax them, you may end up with some result. But based on the results that sorry, you end up with something that can be consistent with what I presented. But based on the results that I presented and the assumptions that I have here, book equity is just a proxy for expected cash flows. We also learned that size and book to market, they can only be associated with the same risks. They're just associated at different levels, as we saw in that picture. And we also saw that S&P returns span HML returns for portfolios formed in high price of states, confirming that this is true. More generally, from a more theoretical side, we also learned that there are no stable economic relations between any particular risk or mispricing. But that's another point. In the paper, I don't talk much about mispricing. In the paper, I actually talk more about mispricing than I talked in the presentation. But everything that I concluded by causation theories associated with risk is valid for causation theories associated with mispricing. And also the same things that I said about people being able to accommodate the results that I have if they make enough assumptions about dark matter is going to be true about mispricing. So you can also come up with a story involving mispricing, in which mispricing just changes in a way that you don't measure, but it's consistent with empirical evidence. Right? But so that's another point. We also find that there's no missing factor related to size of book to market. And this is important because it means that when you do regressions, when you run regressions that rely on size-related portfolios, you're not running regressions that are accounting for any risk. So these regressions do not adjust for unconditional risks, at least. If you run it unconditionally, the regressions are not controlling for any risk. And the reason is that one that I told you when I discussed the correlation hypothesis, that the risks that are going to be associated with size, with price, they're different, right? It depends on which one is the risk that has the highest cross-sectional variance in risk premiums in each state. And that's it.